So let's get to what we're looking at for first unit, and that's power functions. Now, power functions are sometimes called polynomials, by the way, are functions that look like what you're seeing here. I know this looks almost complicated with all these exponents and subscripts and all of that, but really all this is a function that has whole number exponents. So you see numbers here like n, right? Or variables, I should say, like n. Right? And you see another variable here like n minus 1 and n minus 2 and so on and so forth. All a power function is a function that doesn't have like sine and cosine in it, or doesn't have reciprocals in it, like rational functions. Those we'll get to. We'll get to all of those kinds, or exponential functions. All of these functions have whole number exponents. So they're not square roots. None of those. You don't have x to the power of a half. You don't have x to the power of minus 1. You don't have that with a power function. So they're the simplest functions that you can possibly have. We call them power functions or polynomials. All right, so n is a whole number, as it says right there, right? And the coefficients are real numbers. Coefficients of each of these terms are real numbers. So the coefficients can be negative, coefficients can be fractions, the coefficients can be a whole bunch of things, but the exponents are always whole numbers, and that's the point about polynomials. Now, these are examples of polynomial functions right here. Here's a linear function. Well, you learned linear functions back in grade 9. That's your y equals mx plus b kind of thing. And a linear function has like an m of, in this case, a half, and the minus 0.4, that's your c, right? So that's linear. That's a straight linear function. Quadratic functions, which you learned, I think, more in grade 10. Well, those are functions that had an x squared in them. So here is a quadratic function right there, minus 3x squared, etc. That's a quadratic function. We've also, or you should have in grade 11, I looked at the survey a little while and saw to get an idea of how, what you felt about the stuff you did in grade 11. A lot of you might have done it during the pandemic and maybe, probably weren't in class for part of it. I don't know. I probably should have asked that question, but maybe I didn't. I don't remember. Anyway, the quadratic function is the one that has the x squared term. The cubic function is the one that has the x cubed term in it. Does it also have x squared? Does it also have an x? Of course it does. But the x3 is what makes it cubic. And then there's a quartic, just an x4. And then there's a quintic, which has an x5. Does it go higher than that? Of course it does. But we usually have just names for the ones that go up to fifth, what we call degree functions. Right? So I'm going to talk about this function in a little while. Just put it aside here for now. Let's get to leading coefficient. The leading coefficient is a term you probably have heard before, and as the definition says here, is a coefficient of the term with the highest power of x. So if I'm looking at this function right here, the leading coefficient is not the minus 5, right, which it may seem like it should be because that's the first number. The leading coefficient is actually the 2. Why? Because the highest power of x is the 4, right? This is the highest power of x right here. So it means that this is the thing that's going to determine how this function behaves. And the number in front of that, the 2, represents the leading coefficient. What's the first coefficient? It doesn't have to be the leading coefficient. So this minus 5 is not the leading coefficient. 2 is. What's the degree of the function? Okay, I hear a hand coming up. Janaya, please go ahead, please. Please go ahead, please. I don't know why I said please twice. I sure can. And by the way, something that I'm going to encourage you to do is what Janaya just did, and Janaya's done this before, so I'm going to compliment her. Anytime there's anything that I've said which you didn't either hear or didn't understand, please stop me and ask me to repeat it. I have no issue with spending more time going over stuff that people need me to go over. So please do exactly what Janaya just did. So I'll go over what she just asked about, which is this. The leading coefficient is not the first coefficient. Coefficient, of course, is the number in front of the x, the constant in front of the x. So the leading coefficient is the coefficient of the term with the highest power of x, right? That's what it says, with the highest power of x. So the highest power of x in this case is x to the power of 4. There's an x to the power of 3, but that's not the highest power. The highest power is the x to the power of 4. So the number in front of that is my leading coefficient. This is my leading coefficient right here, the plus 2. Does that help, Janaya? Does that make sense now? Yeah. Okay. Okay. So your question was, I was repeating your question, is if I had a whole bunch of other terms in my polynomial, I'd had an x to the 5 or an x to the 6 or something like that. Would the number in front of that still be the leading coefficient? The answer to that is yes. It's whatever the highest power is. And that takes us, by the way, to the degree of the function, because the exponent of the highest power is what gives you the degree of the function. So in the case of this one here, this is a degree 4, right? This is a quartic function. It's quartic because the highest power, right, is not the first power, which is 3, it's the 4. 4 is obviously bigger than 3. So that makes this function a quartic function. And that means that the 2, as we said before, as to Janaya's question, is what is the leading coefficient, because that's in front of the highest power. So the highest power, in this case of 4, is what tells you what a degree is. So in this case, this is a quartic function, a degree 4 function. And the number in front of that is a lead coefficient. Okay? All right, let's move. Okay, you're welcome. So let's move on. The constant term. Well, that's something you learned back in grade 9 as well. It's a number or the term that doesn't have a variable. And when I talk about variables, of course, I'm talking about the x's or the, whatever the letter is in the function. It doesn't have to be an x, it could be any other letter. But whatever is the variable, if there's a term without a variable, then it means that that becomes a constant term. So here are my constant terms. That's the -9, the -4, the -8, the 9, and the -0.4. Those are my constant terms. Guess what? This particular function here, the one that I was referring to before, does not have a constant term, right? So the constant term could be referred to as 0. That's your constant term. All right, line symmetry. What is line symmetry? Well, you've heard of symmetry before because I'm sure you've heard of things like the axis of symmetry. It's just a line that divides a graph in a way that what's on the left-hand side of that line is the same as what's on the right-hand side of the line. It's a mirror image of each other. That's what a line of symmetry is. It's just a line that separates. Yes, no, please go ahead. Well, it depends because a line of symmetry doesn't have to be about the y-axis. A line of symmetry could be along the x-axis. That is possible as well. You could be symmetrical in different ways. So I wouldn't say that it is necessarily about the y-axis, right? Because there are other lines that can be the what's called the axis of symmetry, right? Right. So your question was, you've heard that line of symmetry is symmetrical about the y-axis, and my answer was that symmetry can have different forms. And in fact, we have line and we have point. We're going to get to point symmetry in a minute. Line symmetry, and it says there in the definition, it's a vertical or horizontal line. As you know, the y-axis is a vertical line, but you can have a horizontal line as well, which is an axis of symmetry. So you can have symmetry along the x-axis. That is entirely possible, where the top half is a mirror image of what's on the bottom half. So there you go. All right. So line symmetry is one kind of symmetry, but you also have point symmetry. That's a different kind of symmetry. A point symmetry is when the figure maps onto itself after a rotation of 180 degrees about a point. I'll give you an example. I sometimes use a graphing program to show it, but let's just stick with this. Let's say I had a function that looked something like this, right? And one of the things you're going to learn very, very quickly, you probably have figured this out already, is I don't write very well and I don't draw very well. So you're going to have to use your imagination a lot with me. This doesn't have line symmetry in the sense that there is no line I can draw horizontal or vertical where one side is exactly the same as the other. But think about this. If I were to take this line that you're looking at right now and put a pin right here in the graph, right at the origin, and twist it through 180 degrees in either direction. So this part here, right at the top here, would be moving, let's say, this way. Oh, well, that looks horrible. Horrible, horrible. Even me, I mean, I know that that's horrible. All right. Let's say this thing here was going to rotate this way, and this thing here was going to rotate this way. Right? Eventually, you'd end up with a graph that looks exactly the same as it does right now, if that turn that you did was 180 degrees and the center of the rotation was right here at the origin. And that's what point symmetry is. Point symmetry is when you twist something around 180 degrees around some central point, that at the end of a 180-degree rotation, it looks exactly the same as it did before. Okay? Yes, Jeremiah, please go ahead. Okay, so your question is, can a graph have, sorry, go ahead, say it again. That's a very good question. So your question, I'm just repeating your question because I want it to be on the recording and your voice is not on the recording. Can a graph have both line and point symmetry? I've actually never thought of that before and I've never seen one that does have both, right? So it usually is either one or the other. And later on in the course, we're going to talk about odd functions and even functions, where odd functions tend to have point symmetry and and even functions tend to have line symmetry. But I've not seen one that has both, but that doesn't mean that they don't exist. That's not Mr. Kamak declaring that as being an absolute. I'm just saying I've never seen it, but I guess and that's a very good question for me to explore and see whether that is in fact possible at all. Yes, sorry, go ahead, Jeremiah. You're going to say something else. Mm-hmm. Oh, I see what you're talking about. If it was a flat line, if it was just a straight horizontal line, is that what you're thinking? Okay, so let me think about that a second. That would definitely have line symmetry, and I guess that would have point symmetry as well. So there you go. Right? That's an actual good example there. But it's a good thing that students bring up stuff like that because I never thought of that before, and that's actually a good point. Okay, so let's move on. Thanks. So let's move on. So we talk about lines, we talk about point symmetry. We need to talk about interval notation because is there a graph that, okay. Yeah, so okay. So I'm just looking at the chat as well. So one of the things that we're going to have to get used to in this course is the fact that, let me just erase this stuff here so we have some more room for writing here, is the fact that some answers aren't just simply 9 or 7 or minus 52. That's not how you answer some questions. Some questions are inequality questions, and the answer to an inequality is another inequality. Okay, so let's say, for instance, you're asked, where is this graph greater than zero? That's an inequality. So you may have to answer that question by saying it's greater than zero from anywhere from 6 onwards. So that's another inequality, anything greater than 6. So how do you write answers like that? How do you put an interval as an answer? An interval meaning everything that is within these boundaries. That's what an interval is. By the way, I will give you your break at 11:15 so that everybody can go stretch and go, bathroom break, all that good stuff. So we're about 9 minutes away from that. All right. So as an inequality is one way to write an answer. So you're saying that your answers for this question, so I can give you a question and say, solve this. And it's not that I'm asking for the answer of 6 or 10 or 52. It's everything between these two boundaries. The answer is between -2 and 3. And look at how this is written. So I'm just getting your attention on this thing right here. You'll notice that it's anything between -2 and 3, but it says x is greater than or equal to -2. So -2 is included in that answer, right? Are these lessons going to be posted after the class? Yes, Caleb. I am recording right now, as I said, and I will be posting the recording on YouTube. And I'll give you a link in the calendar. So you can always consult the calendar on any day that you want to go with that lesson, and the link to the recording will be there. Okay. All right. So there you go. So between -2 and 3. So what we're saying is that your answer is somewhere between or anything between those two boundaries, including -2, but not including 3. Because this says less than 3, but not including 3. That's a different thing from greater than or equal to 2. Greater than or equal to 2 means that -2 is part of your answer, but the 3 is not. Anything just under 3, but not including 3. So one way that writing is using the inequality, which is what I'm pointing to with the blue arrow. You can also use brackets. So you notice that I have a square bracket on the -2, followed by a comma, followed by the 3 with a round bracket. The square bracket means that I am including the minus 2. So it's the same answer as the one before. These two answers are both saying the same thing. The minus 2 to 3 is the same minus 2 to 3 from the first one, because the minus 2 is included, whereas the 3 is not. The 3 is the boundary, so it goes up to 3 but does not include the 3. All right? Another way of expressing it is to use a real number line. So you look at this number line and you see me doing the same thing. I'm showing you the same result or the same answer from the first two, which is going from minus 2 to 3, except that the minus 2 is included. That's why that dot is filled in, but the 3 is not. So I'm going anywhere between this whole region right here is included, and it also includes the minus 2, but does not include the 3. So although 3 is the boundary, that's not to be included in your answer. And we'll see why that is useful later on. Okay, so all three of these, I'll put a circle around them. All three of these are giving you the exact same interval. Every one of those means exactly the same thing. One with inequality signs, one with brackets, bracket notation. You'll be using that quite a bit. And the other one with a number line. They all mean exactly the same thing. Sometimes we need infinity symbols though. So let's say, for instance, you'll see one response here which says x is greater than or equal to 5. So I'm not going to use a number line for that. I'm just going to show you that as one way of representing it with an inequality. But I can also represent that with brackets, because x being greater than or equal to 5 means I'm going from 5, but I'm not stopping on the other end. I'm going all the way to infinity. I'm going all the way to the end of the number line, wherever that is. It's a concept that I know sometimes people find very abstract. What is infinity? Well, it's that thing at the end of the number line. Number line doesn't stop. So these two things are saying the same thing. This x is greater than or equal to 5 is the same as 5 to infinity. Jeremiah, please go ahead. Okay, you never, so you're talking about square brackets on the 5 and the infinity. You never, and I want to make sure I repeat this. You never ever put a square bracket on infinity, because infinity is not a number. Infinity is this abstract concept. Whenever you're putting a square bracket on one side of an interval, you're saying that it's at that particular number. But infinity is not a real number. It's a concept. It's what you have when you get out to the end of the universe. It's just this abstract sort of, what's out there at the very end. So we never, and I'm going to repeat it now, you never put a square bracket on infinity. Infinity always has a round bracket. And thank you for that question. So you're welcome. So both of these things mean the same, right? Both of these things are saying exactly the same thing, but they're using different ways of expressing it. One is saying greater than or equal to 5. The other one is saying greater than or equal to 5. One is using the greater than or equal to, and one is using the brackets. Square on the 5 because it says or equal to 5. If I were to write this, it would be saying something different. It would be saying 5 to infinity, but 5 is not included. That's a different answer from the one I had before. Okay, now we're at 11:12, and we're going to be going over some graphs in a few minutes. I'm loath to sort of start working on the graphs so close to the break. So let me just quickly mention these things, which will become a lot more, should make a lot more sense to you once we start looking at the graphs. It says that even powers only go in one direction, up or down, right? Odd powers will both go up and down. What does that mean? That's what we're going to be explaining. So I'm going to come back to these things on where it says power functions in a few minutes. Knowing the power and the leading coefficient, here's the main thing that's going to become evident when we get to the next page. Knowing the power and the leading coefficient can tell us what's called the end behavior of a power function. So we're going to be talking about quadrants in a little while. Quadrant this to quadrant that. So quadrant 3 to quadrant 1, etc., etc. So even before we do that, let me just quickly remind you right? I put a brand new thing on the screen here, brand new page on the screen. I use a smartboard a lot. I love the smartboard. That generally refer to this on the Cartesian plane, refer to this as quadrant 1, and we go in a counterclockwise direction. Refer to that as quadrant 2, and refer to this as 3, refer to that as 4. Okay? So if you bear that in mind, when we actually start looking at the graphs, and we're going to start talking about how these polynomials tend to behave at their ends. End behavior doesn't refer to, well, I'll tell you exactly what it refers to. End behavior refers to what happens at either end of a polynomial, because it has a very predictable pattern of behavior. And as it says on the previous page, that pattern of behavior has to do with the leading coefficient and the power. And the power here refers to the degree of the function, whether it's an even degree function or an odd degree function. Okay, so it's 11:14. I'm going to give you a whole extra minute of a break today. So I'm going to stop my recording